Hi everyone, in this video we're going to look at transformations, in particular the dilation, and looking at the difference between dilation from the x-axis and dilation from the y-axis. So it's a bit easier to explain when I can actually have the graphs in front of me. So what I've got here is the graph. If you look on the left-hand screen, y equals ax squared. So the value of a is just our dilation factor. So if you look at the graph, actually I might just put back on the original. So that's y equals x squared, and you can see as a changes, okay, your graph dilates. So it either becomes wider or narrower, just like that. Now it can be described as dilating from the x-axis or dilating from the y-axis. You can actually say both, but just one or the other. So you can't say it's dilated by a factor of this from the x-axis and dilated by a factor of this from the y-axis. It's just easier to say it's either dilated from the x or dilated from the y. Now, when you decide which one, it doesn't really matter, although sometimes it's easier to find the dilation factor from the y-axis than it is from the x-axis, or vice versa, just depending on what you're dealing with. Okay, so I'm going to put this back to 1 because we're going to have a look at this soon. All right, let's get back to my screen. So I'm going to do 2 examples. My first one is going to be just a parabola. So we're going to go from y equals x squared, and we're looking at the transformations to get y equals, I can't remember what I did, 4x squared. All right, so what did we do to get from y equals x squared to y equals 4x squared? Now, if we're doing it without graphing, all right, so what am I going to do? I'm just trying to figure out what color to do my writing in. Okay, I'll do it in blue. Okay, so remember when you're looking at your new image, we rewrite it as y dash equals 4x dash squared. Now I like to put just the x dash in brackets, just so we don't get the dash and the squared mixed up and then maybe make the mistake of seeing it x to the power of 12. All right, so we're just seeing that as the image of x and the image of y. Now, it does depend on whether you want to do a dilation from the x-axis or a dilation from the y-axis. So just looking at this, because this is a basic parabola, I can see we've had a dilation of 4 from the x-axis. So let's go ahead and do the working for that, and then I'll show you the other way how we can do it for dilation from the y-axis. And you wouldn't believe it, I'm actually talking with my hands, and you can't even see my hands, but it doesn't matter. Okay, so if we're doing a dilation from the x-axis, we know we're going to have a change on our y. So let's just divide both sides by 4, so they cancel out, and get back to blue. So we've got y dash, don't know why that y started out purple, y dash over 4, let's just rub that out because I like to be consistent. And our x doesn't change, so it's just going to say x equals x. So no changes on our x, but our x dash on 4 is equal to y. So we just need to say, well, what is the image of y? It is equal to 4y. So the image of our original graph is x 4y. Right, so remember I said before it was a dilation of factor 4 from the x-axis. Dilated by a factor of, I hate it when it does that. Sorry. Of 4 from the x-axis. And I can't spell. There we go. All right, so that just means it's been stretched. So let's have a look on our graph. So I'll just go back to Desmos, and I'm going to change a to 4. So when a is 4, all right, there we are. Okay, so the blue graph is our original graph, y equals x squared. And then we've dilated by a factor of 4 from the x-axis. So it's kind of stretched. All right, it's become narrower. So that's the red graph. All right, let's go back and let's do it from the y-axis. So if I'm doing it from the y-axis, and just because I love color, let's do it in a different color. So I might do this one. Oh, yellow's a bit hard to read. Let's do it in orange. So we start off with the transformed graph again. Okay, so there we are. But this time, because our transformation is on the x, I'm going to be looking at the x. Now, you can't look at your transformations, your dilation from the y-axis until you've substituted for x. So at the moment, this is 4 times x squared. What we want to have is that 4 inside that bracket. Okay, so I did put a bracket there just to differentiate the squared from the image of x. But if I'm putting that 4 inside the bracket, it's going to come in as 2x. All right, so expanding that bracket would give me 4x squared. So when I put it in, I get 2x squared. All right, so it's the same thing. It's just going to enable me to do, look at the transformation. All right, so let's solve it. So I'm going to choose a different color than pink. Let's do green. All right, so y hasn't changed. So y dash is equal to y, but your x, got the dash, 2x dash is equal to x. Okay, so in our x position, so in this position, x, we now have 2x. So I don't know whether you could see that. So doing lots of highlighting and colouring is now 2x. All right, so what are we squaring? We're squaring 2x. All right, and let's just put that little dash back on there. So I just need to rearrange this to get my image of x on its own, which is the same as x on 2. So my image, my new point, is going to be x on 2, comma, y. So you can see now we have a dilation on our x. Sorry, we have a dilation from our y-axis, but the factor is applied to the x. So dilated by a factor of 1/2. Okay, so that's the coefficient of x from the y-axis. Okay, so we've got the same equation, so y equals 4x squared, but we've written the dilation differently. We can write the dilation from the x-axis or the dilation from the y-axis. So let's go back to Desmos. All right, so you'll see on the left-hand screen, I've now introduced a third graph. So it's my purple one. So let's put them all back in the same spot. So if I let a equal 1, so if you just see me moving this pointer, b equals 1. So everything is equal to just y equals x squared. And as soon as I start changing them, they move. All right, so remember what I had before. My value of b was 2. So remember I had to put it inside the bracket. There it is. And my value of a was 4. So I'm going to make that 4. And you'll see it's slowly going to become the same line. So the blue curve is y equals x squared. We can only see the purple line, but underneath the purple line is the red line. And you can see that they're equal. All right, so I've just proven that y equals 4x squared and y equals 2x all squared are the same thing. And when you think about it, squaring 2 gives you 4 anyway. But let's have a look at the dilation factor in a bit more detail. So parabolas are really good because we can actually find points on the graph quite easily. So remember the blue graph is my original one, and I don't know whether I can draw on here. I don't think I can. Let's just see what happens. Oh, can I make you stay? Let's see if I can right click. No. All right, so we can see there is 1, 1. I probably can, but I won't spend all the time trying to figure out how to do it. All right, so if we're doing a dilation from the y-axis, so from our blue graph, so remember It's a dilation factor of 4. So we would expect for our red and our purple graph at x equals 1, y to equal 4. So let's just have a look. Go back up. And you can see it's just there. All right, so 1, 4. All right, so we've gone from 1, 1. So the x doesn't change, if I can find the point. And then we're going up to 1, 4. So you can kind of roughly see that I'm getting there. It's just, trying to find the point. So we can also say, well, what other point goes through? So this point here, going nicely through our grid line. So that point there is 2, 4. So if we were to look at the next value at x equals 4, so 4 times 4. So if we keep going up in a straight line, now this is going very, very high, we would expect it to be 4 times 4 is 16, and you can see it is there. All right, so we've had a dilation factor of 4 from the x-axis. Let's just go back. All right, the other way, so if I just refresh your memory, we could have had a dilation by a factor of a half from the y-axis. So let's go back to my Desmos. Okay, so remember on our blue line, we're going through, actually might not do 1, 1. Let's do 4, 2. So we're up here. So remember the blue curve is our y equals x squared. So when we're doing a dilation from the y-axis, our y-coordinate doesn't change, but our x one does. So remember we're doing a half. So a half of 2 is 1. And there's that point there, 1, 4. If we go up and find another point, okay, so here at 3, 9, your y coordinate will stay at 9, but half of 3 would be 1.5. So let's see if we can get 1.5. Oh my gosh, it's like winning Tatslotto. 1.5, 9. All right, so we're half every time. There's another one. 4, 16. So half of 4 is 2. So we'd expect this point to be 2, 16. All right, there it is. So you can work it out either way. Now this one here that we just did wasn't overly difficult, all right? But sometimes we get harder ones, and the next example I'm going to do is a hard one. So don't go and think, oh, okay, I've grasped it now, because the next one is harder, and it kind of emphasizes why you would choose one over the other. All right, but it's probably good that you understand how to do both. All right, let's scroll down to here. Now I've written it down so I don't have to think on the spot. And I think this one was actually taken from your textbook as well. So let's put it in. Actually, maybe this is one I did in the class as well. Can't remember. All right, so this time we're going from y equals 1 over x squared to y equals 5 over x squared. All right, and that is our image. So I'm just going to put a little dash there, and I probably should have put my x in brackets, so I'll do that. Very hard to fit it in. All right, so from memory, I think I did do this one, but I'm going to assume that I haven't done it. So I'm going to do a dilation from the x-axis. So we're going to just work with the y. So to get rid of the 5, I'm going to divide both sides by 5. So we're going to have y dash over 5 is equal to 1 over x dash squared. So my y dash over 5 is where our y was. So that means y dash is equal to 5y. And our x hasn't changed. All right, so x dash is just equal to x. So when I'm looking at the coordinates, we're going to have x is unchanged, and we've got 5y. So that's a dilation of, actually, I can never get the phrase right, dilated by a factor of, let's just cross it out, dilated we'll get there. Dilated by a factor of 5 from, oh, come on, give me a break, from the x-axis. Okay, so let's have a look at what's happened there. So let's go back to our graph. Okay, so obviously we're not doing a parabola now, but here's one I prepared earlier, truncus. All right, I'm going to get rid of just that one for now. And I might just move that up so we can, oh, sorry, move that up so we can see it straight up. So this time my red graph is my original truncus. So we can see that there, 1 over x squared. And my blue graph is when I'm changing the value of a. All right, so there it is. If I make it 5, all right, so it's dilated by a factor of 5 from the x-axis. So again, what we can do is choose a point on our graph. So we're going to be going up by a factor of 5. So let's have a look at these two lines. It's a bit hard because truncuses get very steep very quickly or very flat very quickly. So to compare them is a bit hard. So let's have a look here. So our red line is our original one. So this point here, 2 1/4. So remember the x stays the same, but the 1/4 is multiplied by 5. So 5 times 1/4 is 1.25. So hopefully that's what we're going to have here. Come back and let's go up a little bit. Hold on, let's try again. No. There we go. All right, so you can see how you get 1 1/4. All right, so 1/4 times 5 is 5 1/4 or 1.25. We can also see down here at 4, so we've got a very small number down here. Let's just go, can go slightly up a little bit. There we go. 4, 0.063. What would that be? Times 0.063 times 5 is about 0.3, maybe just over. And then you can see it there, thereabouts. All right, so we've increased it by a factor of 5 from the x-axis. All right, so let's do it from the y-axis. Now this one is why a good example of why you probably wouldn't do it, because it is a little bit more complicated. So let's just rewrite our equation. So we've got y dash equals 5 over x dash squared. So what I want to get is, like before, the value in here. All right, so if you think about that being a function, f of x, I'm substituting in an x. All right, so I've got to put something in there. At the moment, I've got this 5, so I've got to manipulate this fraction. So the 5 is in that bracket with the x. Now, if you think of your fraction rules, okay, so if I had, this is the same as 1 over x squared times 5. Now remember, when we do dividing fractions, we keep, change, flip. Now if I want to go the reverse of that, I can do keep, change, flip again, but the 5 is written as 5 over 1. So I can say, well, that's the same as doing the dividing by its reciprocal, 1/5. So effectively what I've got now, see how I told you it was more complicated, is we're going to have to put that 1/5 down the bottom. So I'm going to have x squared over 5. Now at this point, I still haven't substituted in for that x because that 5 is not a part of that square. All right, the square is just applied to the x, not to the 5. I want everything to be taken to the square, power of 2, taken to the square, taken to the power of 2. So if I put the x over 5 in my brackets and square it, I've now changed that value of 5 and I can't change it. So you're going to say, well, if I was to square that 5, I'm going to get 25. So, but I want it to be 5, so I'm going to have to take the square root of 5 because squared of a square root, you're just left with 5. Okay, so I haven't really changed the value of anything. I've just made it so I can see that dilation. All right, so now we can start looking at the image. So y hasn't changed. So y dash, the image of y is still y. But, and I forgot to put my dash on my x again. Get back on there. And then I've got my x dash over the square root of 5 is equal to x. So x dash is equal to the square root of 5x. So when I'm looking at the image, it's root 5x, y. So it's been dilated by a factor of square root of 5 from the y-axis. So see how much more complicated that is? So, you know, when you choose one over the other, it's probably because it's easier to do. All right, so let's just go back to our graph. Okay, so remember we've already seen, oh, sorry, I just pressed a button with my arm. We've already seen a dilation from the x-axis. So let's just have a look and make sure we're doing it right from the y-axis. So where am I? Let's go back here. Okay, so my value of, whoops, I got to put my graph back on. Okay, so let's put the graphs back together. So I'm going to make them all the same for now. All right, so you'll notice I've got y equals a on x squared and y equals 1 over bx squared. So when I change the a to 5, and then I'm going to change the b to 1/5, which is the same as 0.2, and you'll notice they start becoming the same line. All right, now we're looking at just the dilation factor. So can I just get rid of that so we can have a little bit of a better look? So let's choose this point here. This is our original 1, 1. Now, if we've been dilated from the y-axis, that means our our y-coordinate stays at 1. All right, so it's still going to be 1, but x has been dilated by a factor of root 5. So 1 times root 5. Now, we're not going to have exact values here, but we'll get the calculator in a sec. It's around 2 point, can I get exactly to 1? Oh, come on, seriously. All right, so it's around 2.2. Okay, let's get the calculator. And I've probably already got it on the calculator. Where's my calculator? Okay, so the square root of 5 is 2.23. Okay, so I couldn't get it exact. Let's try again. Oh, so close. Okay, can't quite get it. All right, so I've just done it on the calculator because I can't get 1 exactly on here. So when I solve for y equals 1, you can see you get 2.236, okay, which is the same as the square root of 5. And if I had it in standard form, not decimal, you can see it's there, square root of 5. Now, when we're at, say, let me just think. All right, it's probably a bit harder to do because we're not going to be at many points again. What have we got? Anything else? Here we go here. Nah. So let's just choose another point. Okay, let's choose this point here. So we've got roughly, say, 3, and it's just below 0.6. Okay. So if we're multiplying 0.6 by root 5, we should end up with this value here, around 1.29. So let's go back to the calculator. So what was it, about 0.6 times root 5? Oh, let's do decimals. 1.34. Let's just double check. All right, so I did round up a bit, but you can see, hopefully you can trust me, that it's pretty much been increased by a factor of √5. So we're going by a factor of √5 from the y-axis. All right, so we'll just go back here. It's usually easier to tell from a graph the dilation from the x-axis, but you do need to know dilation from the y-axis. So doing mapping like this is very helpful. All right, so make sure you kind of understand how to do that, and please let me know if you need more examples. Okay, bye.